Space ref Earth today. Strong winds power electric fields in the upper atmosphere. Zero comments, so this might be quite a fresh article. Using observations from NASA's ICON mission, scientists presented the first direct measurements of Earth's long-theorized dynamo on the edge of space, a wind-driven electrical generator that spans the globe 60-plus miles above our heads. The dynamo churns in the ionosphere, the electrically charged boundary between Earth and space. It's powered by tidal winds in the upper atmosphere that are faster than most hurricanes and rise from the lower atmosphere, creating an electrical environment that can affect satellites and technology and volcanoes and seismic activity on Earth. The New York published today in Nature Science improves our The new work published today in Nature Geoscience improves our understanding of the ionosphere, which helps scientists better predict space weather and protect our technology from its effects. Launched in 2019, ICON, short for Ionosphere Connection Explorer, is a mission to untangle how Earth's weather interacts with the weather in space. Radio GPS signals zip through the ionosphere, which is home to auroras and the International Space Station. Empty pockets or dense swells of electrically charged particles can disrupt these signals. Scientists who study the atmosphere and space weather have long included Earth's dynamo in their models because they knew it had important effects. Really? But with little information, they had to make some assumptions about how it works. Data from ICONS is the first concrete observations of winds fueling the dynamo, eventually influencing space weather to feed in those models. ICON's first year in space has shown predicting these winds is key to improving our ability to predict what happens in the ionosphere, said Thomas Immel, ICON principal investigator at University of California, Berkeley, and lead author of the new study. This data visualization shows the ICON spacecraft in orbit around Earth. The green arrows show how the strong high-altitude winds known as atmospheric tides detected by ICON's MITI wind imager. These winds are not uniform and can be altered by changes in the lower altitude atmosphere. This, in turn, changes the particle motion high in the ionosphere. Changes in plasma at 370 miles above Earth's surface was also detected by ICON, as shown in red. Magnetic field lines are shown in magenta and turn yellow as measurements of winds detected by MITI. Green arrows influence the direction of plasma. In most generators, these components are bound tightly so they stay put and act predictably. But the ionosphere is free to move however it likes. No, it's not. The current generates its own magnetic field, which fights Earth's magnetic field as it's passing through, Immo said. So you end up with a wire trying to get away from you. It's a messy generator. Following the whims of the ionosphere is key to predict space weather's potential impacts depending on which way the wind blows. Plasma in the ionosphere shoots out into space or plummets towards Earth. This behavior results from the tug of war between the ionosphere and Earth's magnetic field. Why has there been a war? There is no war going on. It's nature. The dynamo, which lies in the lower end of the ionosphere, has remained a mystery for so long because it's difficult to observe. Too high for scientific balloons and too low for satellites. It has eluded many of the tools researchers have to study near-Earth space. ICON is uniquely equipped to investigate this part of the ionosphere from above by taking advantage of the upper atmosphere natural glow to detect the motion of plasma. ICON simultaneously observes powerful winds and migrating plasma. This was the first time we could tell how much the wind contributes to the ionosphere's behavior without any assumptions, said Astrid Maut, another study co-author and ICON scientist at the National Center for Atmospheric Research in Boulder, Colorado. Only in the past decade or so, Immel said, have scientists realized just how much those rising winds vary. The upper atmosphere wasn't expected to change rapidly, but it does, day to day. We are finding this all due to changes driven up from the lower atmosphere. Maybe not. Ever heard about Christian Berkland? Wind power. Familiar are the winds that skim the surface of Earth, from gentle breezes to bracing gusts that blow one way and then the other. High altitude winds are a different beast. Oriboran. From 60 to 95 miles above the ground in the lower thermosphere, winds can blast in the same direction at the same speed, around 250 miles per hour, for a few hours at a time before suddenly reversing direction. By comparison, winds in the strongest Category 5 hurricane steer at 157 miles or more. These dramatic shifts are the result of waves of air called tides, born at Earth's surface when the lower atmosphere heats up during the day, then cools down at night. The surge through the sky daily carrying changes from below. The farther the atmosphere stretches away from the surface, the thinner it becomes and the less turbulence there is to disrupt these motions. That means small tides generated near the surface can grow much larger when they reach the upper atmosphere. Changes in the winds up there are mostly controlled by what happens below. ICON's new wind measurements help scientists to understand these tidal patterns that span the globe and their effects. Tides ripple up through the sky, building in strength and growing before gusting through the ionosphere. The electric dynamo whirs in response. The scientists analyzed the first year of ICON data and found high-altitude winds strongly influenced the ionosphere. We traced the pattern of how the ionosphere moves, and there was a clear wave-like structure, Harding said. Changes in the wind, he explained, directly corresponded to the dance of the plasma 370 miles above Earth's surface. Half of the motion of the plasma can be attributed to the winds that we observe right here in the same magnetic field line. That tells you it's an important observation to make if you want to predict what plasma is doing. ICON's first year of observation coincided with solar minimum, the quiet phase of the Sun's 11-year activity cycle. During this time, the Sun's behavior was low, constant hum. We know the Sun's not doing much, but we saw a lot of variability from below and then remarkable changes in the ionosphere, Immel said. That told the researchers they could rule out the Sun as the main influence. Oh, man. Oh. As the Sun ramps up to its active phase, scientists will be able to study more complex changes and interactions between space and Earth's atmosphere. Immel said that he is excited to have this confirmation of long-held ionosphere theories. We found half of what causes the ionosphere to behave as it does right there in the data, he said. This is what we wanted to know. Still, Maute said, this leaves room to explore what else is contributing to the ionosphere. The Sun. But I want to point out one thing. NASA's use of the word plasma. I have never read any paper like this kind of short one, where they use the word plasma so many times. One. Yeah, I will count it. I leave it here. I leave a link below. Plasma talking about NASA talking about plasma. Thanks. Bye.